Hello everyone. In this lesson we will look at transformer architecture. So if you haven't watched the lessons on tokenization, decode strategies for text generation and multi-headed self-attention, then I would highly recommend that you watch those lessons first in order to understand this lesson fully. So let's begin. So let's first of all look at the transformer architecture at a high level. So this architecture is taken from the paper Attention is All You Need, and it was published in 2017. So at high level, transformer architecture consists of two modules. One is encoder, other is decoder. So the initial transformer architecture was demonstrated on sequence to sequence language translation task. So let's say we have a text in English, I like movies, and we want to translate it to German. Then its translation would be Ich mag Filme. So first this English or input text is converted into tokens. So this pre-processing will contain multiple things. We will look at it shortly. So at high level, this text will not be directly consumed by the encoder. It will need to be converted to some numeric form. So tokenization will happen here. And there are different tokenization strategies. So you can go ahead and watch the lesson on tokenization to see the details. So this tokenization breaks this input text into different tokens, and each token will have a unique token ID from the vocabulary, and those token IDs are further converted into embeddings. So in the original transformer paper they used embeddings of size 512. So any token, let's say T1, it will be some number of dimension 512 cross 1. So there will be 512 numbers here to represent one token. And there are some further operations like positional encoding, which we will see shortly in this lesson. And after that it goes to encoder. And encoder has different modules. We will look at that shortly in the next slide. And what the encoder does is that it takes the entire sequence of text and it generates a meaningful embedding of that entire text, and that embedding is fed to decoder along with the output. So here output is whatever text is generated till now. So let's say first output is generated, it's ich, and we are in the process of generating the next words. Then here input will be just ich, and all the other words will be masked because in the training we have the entire translated text. So here input is not this input, but whatever is generated till now, that part. And then again similar kind of processing happens on this input as well, and it's fed to decoder along with this embedding, meaningful embedding of the original input text. And there are some further output layers like softmax and some linear layers specific to the task that we want to achieve, and then finally output text is generated. So this is a very high level view of transformer architecture. So let's dive deeper into it. So here this is the encoder part, and this you can see is the decoder part. So here again this tokenization happens, then embeddings for each token ID is calculated, and then we have something called positional encoding. So whatever is the dimension of embedding, so if the sequence length is T, so there are T tokens in the sequence, and then each token will have some embedding, let's say DE, in this case 512. So this output here, input embedding, will be T cross 512 matrix, and then we add to it positional encoding. So when we saw this multi-headed attention, if you recall, we had self-attention stacked together one after other. So in the original paper there were 8 such attention heads. So there, when we calculated those Q and then K transpose and then divided by dk and calculated softmax. So for any given query word, we found its like which other words in the sequence were relevant and how much relevant. Then we did not add any notion of position there. So if we have a sequence I like movies, or whether we have a sequence movies I like, so whether these movies occur at place position 1 or 2 or 3, we were not accounting for that in the self-attention. So here we add the notion like same word occurring at different position adds different meaning, different context to the text. So that info is added using positional encoding, and its dimension should match this dimension in order for it to be added here. So how this positional encoding is done in the paper is that so let's say we have positions. Let's say we have a word. It can occur at position 1. It can occur at position 2, 3, 4. So these are the positions in the sequence, input sequence, at which position this occurs, starting from 1. So they define position like position encoding at a position, let's say position is pause. So POS can take a value of 1, 2, 3, 4, 5, so on. And then 2i. So they calculate using sinusoidal embeddings like sine, then position divided by something called, I'm forgetting the exact number, but I think 10,000 raised to the power of 2i divided by some number, let's say. So if position is 1, this numerator will be different, and for 2i plus 1th position, they were taking cos position divided by 10k raised to the power 2i plus 1 divided by something. So I starts from 0. So initially this I will be 0 and 1, then next will be 2 and 3, and so on. So this position will take a value of 1, 2, 3, 4, and so on. So if a word, let's say cat, occurs at position 1, then its positional encoding calculated using this sinusoidal formula will be different, because this we will be taking sine and cos of different position values. Instead, if it occurs at position 5, it will be some different value. So the goal here is that it should be able to differentiate that if same word occurs at different position, it should add different meaning to the input. So once this positional encoding is added to the input embeddings, it's passed to multi-headed attention, which we had seen here. So we were passing different query, key and value matrices, and then we were generating the output from these multi-headed attention. So again the same output dimension will be generated here, and then this add denotes this kind of skip connection here, so which was similar to ResNet blocks. So here this skip function x is x plus some layer which is there X. So this skip connection denotes that. So in essence it means that here also we have this skip connection. So if this layer does not learn something meaningful, then it will take this whatever was X here, it will be passed to the next layer. So the output of, so add denotes that, and then we take normalization. So here normalization means layer normalization. So it will be normalized across different heads. And then it's passed to feed forward or multi-layer perceptron. And again this skip connection and normalization. And now here we have a meaningful and context aware representation or embedding of this input text. So this text is passed to decoder. So here we have multi-headed attention blocks again, here and here. So here we see additional masked, because masked only means that when we are in the process of training, let's say, and we have generated only, let's say, first word, then we will mask all the remaining words, remaining output, desired output. Because if we don't mask it, then the model actually knows the answer. So it's kind of cheating with the model. So we mask these things. So every other word will be masked. And here we have ik generated till now. Then in the next step, let's say mag is generated. So here in the input we will have ik, mag, and all the other further tokens will be masked. And this embedding of the entire input sequence is passed here. And here this embedding of this masked output is passed. And then we have a couple of multi-headed attention and feed forward. And again we have linear and softmax. And you can change these depending on your task. Let's say you have some classification task, though, so you can adjust it accordingly. And so what it outputs is, so we had already seen in decoding strategies for text generation lessons that it generates probability vector for each token. Let's say it's currently generating third token. So for third token it will generate a list of probabilities of, let's say, 50k, where 50k is vocabulary size. So if vocabulary size is 100k, it will be, the dimension of this will be 100k cross 1. So each value here will be a probability. So let's say 0.0001, then 0.02, 0.3, 0.0000. So the sum of these should be 1. So we see that the highest probability is in this case for second token, and there will be 50k or 100k such values. So depending on the search strategy, whether it's sampling or greedy search or p sampling or top k, we will pick the most likely words as the prediction. So this is how it works. So the output here is for each token this kind of vector. So you can see that it's a costly operation, because for every token you are generating a very large vector size and taking softmax. So this part is costly. So this is the high level workflow of how transformer works. Now let's see. So we had only looked at, this is one encoder block and one decoder block. But in the original paper, there were 6 such encoders and decoders. So this entire encoder and decoder will be repeated 6 times. So this input goes to encoder 1, and then its output is fed to encoder 2, and then encoder 3, 4, 5, and encoder 6. So the structure of all these encoders will be exactly same, just like this encoder. but their weights will be different. So weights are not sharing. So no weight sharing and same structure. So the representation embeddings from this sixth encoder will be fed to all the decoders. So in this illustration, it was fed to this decoder. So instead, it will be fed to all the 6 decoders. And then the output here again we will have linear and then softmax, and then the output probabilities will be here. So again the structure of all the decoders is same and no weight sharing. So this is how it works. And next we have different transformer architectures. So we looked at encoder decoder as it was presented in the original paper, but this is not the only architecture. We also have some encoder only and decoder only architectures depending on the use case. So no single architecture is universally better, but each has different purpose. So like sequence to sequence, we use encoder decoder, and encoder only is generally used in representation models like BERT, where we want to get a meaningful embedding of the text. Decoder only models are generally used in text generation tasks like GPT based models or ChatGPT, which you are aware of. Now let's see some example from the original paper. So here they had shown that so we had seen that we have multi attention head instead of single self attention blocks. So this is attention block 5, this first one, and next one is attention block 6. So if you see in attention block 5, if you see the word law, then the more darker the lines are, there is a strongly it denotes a strong link. So you see that in attention head 5, the word law is strongly related to the law, and here B perfect, these 4, and very less related to these other terms. Also there is some link here to I think opinion or some words here, whereas if you look at the same word in attention head 6, you see that the and law are related, but this B and perfect are not. Similarly, you can look for this application, it's related to its application, whereas in the attention head 5 it's but very weakly related to application and strongly related to B and just. So you can see that it's not redundant to have multiple attention heads. All the heads are learning some different context or relations between different words. So that was it for the transformer architectures. In the next lesson, we will look at the different applications and limitations of transformers.